Good afternoon, everyone. My name is Nizar, PhD student from Saudi Arabia. Today I will present our work on how we can use the dynamic pollen instability of electrostatically actuated MEMS resonator with the multimodal excitation to demonstrate a smart sensor that can, accurately quantify the gas concentration, and if the concentration exceeds beyond a certain threshold value, it will perform a switching on demand. So MEMS resonators are the main building block of many smart sensor applications that cover biomedical, gas sensing, or even detecting ions or electrons. Now, smart sensors are simply composed from the sensing element, which sense the presence of a particular gas, track the change in certain physical parameter, and send this sensing signal to a microcontroller where the logic or the processing is happening. And the microcontroller is pre-programmed if the concentration or the level exceeds a certain threshold value to send an actuation signal to an actuator. It might be an alarm or a solenoid valve to close a certain gas cylinder or something like this. Now, what we are aiming to do here is to use the pollen instability of electrostatically actuated MEMS resonator in order to allow the sensor itself to perform the sensing and send the actuation signal without the need of the microcontroller. And this will help in reducing the complexity and the device size. It will help in reduce the power consumption and the cost of these smart sensors. Now, we will demonstrate the idea on water vapor application for safety reasons and the limitation of our experimental setup, but it really can be easily extended to biomedical application if we functionalize the resonator with a biorecognition layer, or more harmful gases if we functionalize our resonator with thin film that has affinity to that particular gas of interest. Now, towards this, we fabricated our clamp microbeam, and we coated them with metal organic frameworks. We used here this type of metal frameworks, which called HCast1, which is known for its selectivity to water vapor compared with other gases that present in the environment. Now we release our microbeam, and this is the picture of the fabricated clamp microbeam. And as you can see, the noisy gray color on the top of the beam surface represents the coating, which is a bit uniform on the resonator surface. Now, this is the experimental setup that we use to characterize our device. It's simply composed from two flow controllers, one to control the saturated line flow that goes through the bubbler, and one controls the dry line flow. The ratio between these two flow meters will determine the gas concentration inside the chamber. We used a lab view and data acquisition card to generate the actuation signal to actuate our resonator. And then we used laser Doppler vibrometer to track the amplitude change due to the water vapor concentration change inside the chamber. Now, we will start now with demonstrating the concept of pollen instability on a single mode system. So initially, when we characterize our microbeam, we use white noise to actuate the microbeam, where we apply a signal that has frequency component from 0 to 1 megahertz. Whenever any of these frequency matches the mechanical resonance frequency, we'll get the resonance peak. Then we scan the vibration at different points along the beam length to acquire the mode shape, which matches the clamp microbeam mode shape. This will give us, again, an idea on the uniformity of the MOF coating, because non-uniform MOF coating will induce distortion in these mode shapes. Then we started by conducting frequency sweep around the first mode of vibration. While increasing the VC voltage, we started to see what we call the pollen instability. In the pollen instability, the resonator under certain actuation voltages, which is in our case 70 volt, and certain frequency band, will have enough kinetic energy to escape from the potential well, and hence the upper electrode will collapse into the lower electrode. And this will give us an electrical signal that we can use to actuate our devices, or our actuator, that is, might be an alarm or a solenoid valve. Now, we start by demonstrating the concept on a single mode operation. So we start by selecting the operating point where the resonator is vibrating around its equilibrium point. We don't have any instability here. Then we monitor the amplitude of fluctuation over the time to ensure the stability of our operating point due to the noise effect. And the minimum detectable mass that we can see here is below 200 picogram. Now, the difference between the operating point and the pollen band determines the threshold value, after which I should realize the switching action. So we start exposing our resonator to water vapor. Once the concentration exceeds the threshold value, the whole frequency response curve will shift to the left, and the operating point will fall inside the pollen band. And at this pollen band, the upper electrode will collapse into the lower electrode, and this electrical signal can be used to trigger an alarm. Now, the challenge with this technique that using single mode to operate this device, that there is a problem of stability near the bifurcation point. As the frequency approaches the bifurcation point or the pollen instability, the noise effect becomes really significant, and it might cause switching not due to water vapor adsorption, but due to the noise only. As you will see here, operating the resonator away from the pollen instability, we have a stable response. Getting close, we start to see a rapid fluctuation in the amplitude due to the noise only. Now, even getting more close to the pollen stability, you can see we started to realize the switching even if we are not exposing to water vapor. And this is due to the noise effect, which has pushed us toward finding another probe or another technique beside this in order to be able to accurately quantify the gas concentration. So we will have this pollen instability near the first mode to determine the switching, and we should have another probe that can quantify the gas concentration at which the switching is happening. So we started to look at the higher order mode of a single resonator. So any clamp microbeam will have infinite number of modes of vibration. The higher order modes are known for their higher responsivity and higher stability compared with the first mode operated near the pollen band. So we started by conducting the same white noise test to ensure that the resonator is vibrating, healthy and vibrating. We did a frequency sweep near the first mode and the third mode of vibration in our case. As you can see here, I will rely on the pollen band instability near the first mode to realize the switching, and the linear shift in the frequency near the third mode to realize to quantify the gas absorbed on the resonator surface. Now, before going into the experimental detail, I need to ensure that my resonator is really stable in the third mode compared with the first mode. So we operated the resonator at the two modes simultaneously, at the first mode and third mode, and we track the amplitude fluctuation over the time. As you can see clearly here, that the third mode is much more stable compared with the first mode. Even we did the Allen deviation, and the minimum frequency detectable near the third mode is 6 times less than the one near the first mode, which indicate that the third mode is really more stable compared with the first mode, and I can use it as a probe to accurately quantify the gas concentration. Then, as you know, any water vapor or any gas sensor, you need to track the linearity and repeatability of your sensor. So we track the frequency shift at different concentration level, and you can see we got a linear response which confirms the linearity of our resonator. And when we flush, after each exposure cycle, we flush the chamber with nitrogen, we return to the original state. And again, here clearly shows that near the higher order mode or the third mode that we used here, we're getting more improved responsivity of the resonator. In this case, it's 1.5 times. Now, to demonstrate the switching, we take the frequency sweep near the first mode under the operating condition where we can realize a pollen band and a linear frequency response near the third mode. We pick operating point. We will start by picking the threshold gas concentration. So from the previous slide, the calibration slide, I know, for example, at this concentration value, this is the corresponding frequency shift near the first mode, and this is the corresponding frequency shift near the third mode. Okay, that I'm expecting from the previous calibration analysis. Now we pick operating point. The difference between the first mode operating point and the pollen band is exactly 1.8 kilohertz, which is the threshold frequency shift near the first mode. Now, we monitor the amplitude fluctuation over time, and you can see the operating points are really stable, and the third mode is much stable compared with the first mode. Then we start exposing our resonator to water vapor. The whole frequency shift will shift towards the left, and the operating point will fall inside the pollen band, and then I can realize the switch. However, the measured frequency shift near the first mode is exactly 1.8 kilohertz, which is exactly the difference between the operating point and the bifurcation point. But the frequency shift that we measured here near the third mode is 1.6 kilohertz, which is way less than the expected one from the calibration. And this can be attributed to the fact that the shift in the first mode frequency is due to the gas absorption plus the noise effect, which get amplified in the vicinity of the bifurcation point or in the vicinity of the pollen band, while the third mode frequency shift is due to the gas absorption only. And hence, this value can be used, which is 1.6 kilohertz, can be used in the calibration part of using the calibration equation, we can get the accurate concentration value at which the switching happened. And hence we can quantify the amount of gas absorbed in the resonator while still being able to switch when we exceed the threshold value. One can think of the noise effect as a safety factor, that you will always switch before you reach the limit. In conclusion, we demonstrated a smart sensor that can accurately quantify the amount of gas concentration and perform switching upon exceeding a threshold value. And this can, if we could optimize the resonator and track higher order of modes, we can demonstrate a sensor that can sense multiple physical parameters. And if any of these parameters exceed the threshold value, we can perform switching action. Thank you.